Okay, so in reality, if I pull this out and there's a friction force here or some other force, this is going to oscillate, come out to A, and it might go close into the full A over on this side, but eventually it's going to get smaller and smaller, right, and then stop. A graph for something like that would look like this. And this is called damped harmonic motion. Okay. And unless you have a driving force to keep this oscillating back and forth at that full amplitude, then things are probably going to behave like this in nature as opposed to something like this. Okay? So here, the amplitude and the energy decrease with time. And things are damped like this because there's a damping force. Things like a friction force would be a force that damps the motion. And we should still label on here, put your T in seconds and your displacement, maybe X in meters up here. This is a graph of damped harmonic motion. I want you to know what that is, and you'll see in the objectives. Number 3 says construct graphs of displacement versus time for an oscillating system which is undamped or damped. If it's undamped, you have a constant amplitude, like we saw before. If it's damped, that amplitude is going to decrease with time. You're welcome. And the rate that this is decreasing down like this is actually a curve right here going down. I think your book might draw that for you in a diagram or two, but don't worry about that curve. We actually have some math and some equations that we can use to talk about the damping effect going down like this. And don't put this on your picture here, but there's lines that go like this that you'll probably see that do like this. And we can describe the rate that this is decreasing here, but we're not going to do that here in this class. And although your book may show a little bit, they don't get into it into much detail. I just want you to understand the term, what it means to have damped harmonic motion, and to be able to draw this graph. But exactly how quickly it's going to decrease, we're not going to determine that. But we just know that that amplitude will decrease. Those are our two types of graph. Okay. And we really won't be doing that much with these here, but I do want you to know what it is and be able to draw that graph, or recognize that graph if I asked you what kind of motion that was. Okay. Any questions so far? Okay, so I'm going to define our terms for amplitude, period, and frequency in terms of a real wave. Remember, that looks like a wave because that just had something that looked like this. So that would feel like what a wave really looked like on a string. But that was just the math description of that motion. That was oscillatory motion of that spring that was going either left or right or up and down. I'm going to write these definitions relating to a real wave, not just the mathematical description of the wave. So it'll be maybe just a little bit different with, when I'm talking about the math description of a wave over here, and I'm looking on that picture, and I went for one full cycle, I would label that as one full cycle. And you could also represent that as one wavelength, but that wasn't a real physical wave, and so you might not describe it that way in terms of the actual mass oscillating back and forth. Okay? So, and in your book, you're probably going to see these written down also, kind of in two forms, where the language will be just a little bit different, whether it's describing a real wave, or if it's describing the properties of the mathematical function over there that was describing the oscillations of that mass. Okay? So let me just first write down what a wave is, and then we'll define all these properties here in a minute. So a wave here is a traveling disturbance that carries energy from place to place. So a real physical wave is a disturbance of something. Particles in the air when I'm speaking, oscillating back and forth. It could be water with a water wave. It could be a wave on a chain or a string like this. This is a real disturbance of something. The mass of the chain here, the air particles, water, anything like that. That's what the disturbance we're talking about is. And we're going to see in physics 2, for those of you who take it, that things like electromagnetic waves, light, and radiation, you're not disturbing anything, any particles. You don't need a medium to disturb in the same way that we do here. So we call these mechanical waves. There must be some disturbance. And that's disturbance of things like that string or the rope there, the water, particles in the air. That's what's creating the wave, or that's what the wave is that disturbance. And that's where I'm saying this is a little bit different than when I was drawing the graph over here, where that graph really wasn't representing the disturbance of the wave on the string there or anything like that. That was just what the mathematical graph looked like describing that other motion. Okay, is that clear what I mean on the difference between the real wave and just the math function looks like a wave, but it's not a real wave in the sense that these were real physical waves that have these properties here. Okay? And let me just write down some of our wave characteristics. And we'll define here all those terms that you have there on number 1. I'm going to put in parentheses here for all these the variable that we use to indicate the amplitude. We just use a capital A for the amplitude. And that amplitude is just the magnitude of the maximum displacement of an object from its equilibrium position. In your notes, I'm just going to put over here in blue also the units for all these. Amplitude is just the maximum displacement of an object from its equilibrium position. If we're talking about displacement, what units should this have? What's displacement?
Meters.
A distance, a length, so something in meters here. So I'll just add all these units on the test, and on your objectives here, maybe make the note here. When it says define the terms period, frequency, amplitude, and wavelength, in your definition, you should also include the units. So just make sure that I might ask you to also list the units for all these when you write these down for me on the exam. Wavelength we use lambda for, that variable. And it's just the distance between any two successive crests or troughs on your wave. And it's really any two successive points, but it's very easy to look at the peaks or the valleys of the wave to be able to measure the wavelength. If this is a length, then this is also in meters here for our wavelength unit. Frequency, we've already seen, we use a little f for that. So we talked about period and frequency in terms of our rotational motion, and we were looking at circular motion. So the period or frequency was just the time it took to make one revolution in a circle, or the number of revolutions you made per second. Here in terms of waves, it's just the number of waves or cycles per second that pass by a given point during that 1 second. Frequency has units of seconds to the -1 or hertz. We've seen those before also for our units there. And then we already know what period is also. We use capital T for the period. Time for one complete wavelength or one complete cycle to pass by a given point. The parts that I've added on to those statements about passing by a given point are just there because these waves now are actually traveling. We're not just stuck on a circle. I'm talking about moving around once in the circle. The wave could actually be moving or propagating across from here to here. And so you might see your wave kind of propagating across the board like this. And the given point would be, I'm just staring at it right here. How long does it take a wave here to pass by me at this point right here? That's why I'm adding on the part here about a given point. Basically, though, you know period is the time it takes to make one complete cycle, and the frequency is the number of cycles per second. Okay. What I'm adding on this point here, we have to add this on because we're talking about the wave actually moving also, not just simple circular motion. We were fixed on one circle looking at one rotation there around the clock. And it looks like we're out of time. So that's 10:30. Are we done? I know it's not right. It's a week late, and they haven't changed the clocks. And when you guys were in here taking the test, I'm sitting here, I'm like, I've been here for 4 hours. And you guys, there was a couple of people left at the end, and I'm thinking, I got to call time. I got a meeting to go to at 12:30. We kind of rushed people out at the last. So I gave you 3 hours, so I was generous anyway. But I'm thinking, I get over to my office, and James comes in there and starts asking me a question. I gotta go. I'll come back after my meeting. And I walk out, and I realize, the clock says 11:30. And I was thinking it's 12:30. But all the clocks over here in these halls, and I saw someone change the clock over there this morning. They were all, hadn't been fixed. So, that's not the correct time. But time does fly when we're having fun here, right?
Yes.
Oh, yeah.
What's the unit of period?
Seconds.
Seconds. Okay. So just make sure you're able to answer all those. Just know your units for these also when you're dealing with these. I ask you this on the exam, and I want these definitions with these units. This is anywhere from 5 to 8 points, or maybe 6 to 8 points. There's 4 of them, either 1.5 point each, or maybe 2 points each. This is what I consider 3 points, as long as you make sure you remember to study the objectives. Okay. And I'll remind you of this again before we take the test, hopefully, because we usually review the objectives at the end, but there's a time or two that sometimes people just forget to look over the objectives. Okay. You will kick yourself if you lose points on your definitions or some of the diagrams that we have on this test.
Are they multiple choice or fill in the blank?
These definitions here,
Yeah.
these are usually just write the definition just like this. Not usually, because we'll have, this test isn't that long, you'll have time to do it. I could put them in a form of fill in the blank or something, but for these I usually ask for a definition. And I want complete sentences, not just number of cycles per second. Give me a little bit more like I've written here, but basically you know what I'm expecting here with what I just wrote down there, I think, for those definitions there.